Hey everybody, we're going to do an example of building a probability distribution function for a discrete random variable. So let's consider the following situation. So imagine being we've got an anesthesiologist, um, and an odd little quirk turns out is that redheads tend to require more anesthesia for surgery. So suppose a anesthesiologist has two patients they're going to have to deal with some morning, and they are curious what their odds are um, of there being how many redheads they might have to deal with that morning. Okay, so let's make a couple of assumptions. So let's just go with the percentage of redheads in the U.S. is, we'll call it 2%, about 2%. It varies region to region. Let's just use 2% to make this this situation just a nice easy number to deal with. And let's also assume that the patient's schedules are determined randomly, so there's no, the events of one redhead or the other are independent, right? So if there were, say, family members maybe being scheduled on the same day, it might change things, because if one person turns out to be redhead, there might be a better chance of the other one or something, because they're in the same family. But we're not going to have any of that. We're going to consider them independent. So I'm going to create a random variable for this event. I'm going to use R to be the number of redheads out of two patients, right? So just out of the two patients waiting, okay? So when we build a probability distribution function, what we'll have is two columns, one for the values of R and one for the probability of those values. Again, I'm using little r here to represent the particular values that will show up here. Okay, so R can take on, right, none of the patients could be redheads, one of the patients could be a redhead, or both of the patients could be a redhead. Okay, excuse me. So what we need to compute in this column, the probability that there are no redheads, the probability that there is one redhead, and the probability that there are two redheads in our patients. So let's use this space over here to compute those probabilities, right? So I'll just start at the top. We want the probability that R equals 0, okay? And so I don't know this off the top of my head, right? This percentage, you might think to yourself, well, there's 2% redheads, so there's 98% that are not redheads. So we might think about that 98% because we're looking at not or no redheads, but we're talking about two people, and so that changes things. So what I'm going to do is I'm going to create some events that I can break this event up into, right? The probability that R equals 0, this event R equals 0 is the event that both patients aren't redheads. I don't know the percentages of both patients not being redheads. What I do know is the percentage of or the probability of an individual person being a redhead. So I'm going to break this into what it means for each individually. What it means is the first patient's not a redhead and the second patient's not a redhead. So I'm gonna write some events over here. I'm gonna say A is the first patient is a redhead, and B is the second patient is a redhead. Okay. So then this event here, neither is a redhead, becomes A prime. Remember, this is the complement to A, not A, and not B, or B prime. Right. We can use our multiplication rule. Since I said these are independent events, right? I said having one redhead doesn't change the probability of having another one, since we're assuming that the scheduling is totally random. Then the probability of A person not being a redhead means, well, there's 2% of we're letting 2%, we're saying there are 2% of all the people are redheads. That means 98% are not. So if you choose a person at random, you have a 98% chance they are not a redhead. And the same thing applies for the second person. So 0.98 times 0.98 gives me 0.9604. And that's going to be the number we put here. Okay. Let's do the probability. We're going to do r equals 2 next. We'll come back to 1. It's a little more complicated. And there are several ways to figure it out. We'll do it one way, and I'll do another example after this where we do it a different way. But for now, the probability that r equals 2, this is now the probability of A and B, right? The first one's a redhead and the second one's a redhead. That's how we get 2 redheads. So probability of A times the probability of B. Again, if we pick a person at random, there's a 2% chance they are a redhead. So we get 0.02 times 0.02 gives me 0.0004. Yeah, 0.0004. Oh, I miscopied this number here. Sorry, I wrote 5 for some reason. That was a 4 from there. Okay, let's do the one in the middle now. This one is going to be a little bit more complicated. So I'll work off to the side here. We're now trying to compute the probability that r is equal to 1. So this one becomes a bit difficult. There are 2 ways we can have one redhead. The first way is the first patient's redhead and the second patient's not. So let's write that event. Right? So this whole thing is an event in and of itself, right? This is the event, first redhead, second not, right? Or we can have a different event. The first person's not a redhead and the second person is, right? These are the 2 ways in which we end up with one redhead. So first not, second redhead, okay? So we have to consider both of those ways of this happening, okay? So now I'm going to ignore what's happening kind of on the inside of these parentheses and just think of this whole thing as an event. This could be the event, maybe I call this E, is the event that the first is a redhead, the second is not, and maybe I'll call this one F. So then I'm really doing, let's do this off to the side, the probability of E or F is just the probability of E plus the probability of F, right? I don't need to subtract with our addition rule. These are mutually exclusive events. The first person can't be a redhead and not be a redhead, or the second person can't not be a redhead and be a redhead. So this is the rule I get to apply. I'm just applying it to events E and F, which are actually these more complicated events. So this ends up looking like okay. So again, this is like my event E, and this is like my event F. So I'm just doing the probability of E and F, just like I wrote over here, okay? Now that we've got these 2 complicated events separated from each other, let's go ahead and deal with each one on their own. We do a multiplication rule here. And again, I've already said the hair color of the 2 patients is independent, so we can do the simple form of the multiplication rule. There's no conditional probabilities here. So I'm just going straight through my rule. A and B is probability of A and B prime is the probability of A times the probability of B prime. And then this one is the reverse. All right, so the probability of A being a redhead is 0.02. The probability of B not being a redhead is 0.98. The probability of A being not a redhead is 0.98, and B being a redhead is 0.02. This works out to be 0.0392. Okay, and so that completes our probability distribution function. Okay, and now we have a complete description of the variable R in terms of the probabilities of all of its values. Let's notice if we add these up, 4 plus 2 is 6 plus 4 is 10, carry the 1, we get 10, carry the 1, we get 10, carry the 1, we get 10, we got a 1 in this column. They sum up to 1, okay, as they should. They're all between 0 and 1, and they add up to 1, okay, and that is one of the conditions on those probabilities, okay. This gives us a little hint as to another way we could have approached this problem. And we'll do this in our next example. I'll do that in another video, but I'll just mention this probability over here, R equals 1, was much more complicated than these two probabilities. Here's a nice case where we could have stopped right here and noted that before we knew this number, we knew that the 3 of these had to add up to 1, so we simply could have subtracted these two values from 1 to find this value. Okay, because we know they have to add up to 1. So that's a little trick that we can use if we want to complete our computations faster. Sometimes it's faster to do that than, for instance, this more complicated situation. Okay, but we'll do that one in another video. That will be it for this one. Thanks, everybody.